Welcome back to the lectures on chemistry and the lectures on molecular spectroscopy. This is the last week of this particular course, and what I propose to do is to give you some topics for you to think about along with one more tutorial, but one of these topics will definitely be also part of the examination, namely Raman spectroscopy. Raman spectroscopy is the important spectroscopy which was discovered by Professor Chandrasekhara Venkata Raman, Sir C.V. Raman. He won the Nobel Prize in 1930 for his discovery of the effect by what is called as the scattering effect. It's unique in the entire molecular spectroscopy in that it studies the scattered light, whereas every other branch of spectroscopy that I have taught you so far studies either the absorbed light or it studies the emitted light. And the scattered light is usually studied by passing the radiation through the sample, but looking at the light scattered from the sample at 90 degrees to the sample tube. So we will see a little bit of that, but in order to understand even the rudimentary aspects of Raman spectroscopy, one needs to understand what is called the concept of polarizability. Polarizability is not easy to describe even in elementary terms or without non-mathematical terms. Therefore, what I would do is that this segment of the lecture, I will not talk about Raman spectroscopy, but I will introduce you to the idea of what are called tensors. You already have been using tensors in an indirect fashion, in the sense you have been using moment of inertia. You have been using it as 3 components for asymmetric top, 2 components of moment of inertia for symmetric top, and 1 component for spherical top. But those are what are called the principal moments of inertia, and they are special quantities. Moment of inertia as is what is known as a second-rank tensor in mathematical sense. In the same way, the polarizability of a molecule, which is the extent to which the molecular electronic distribution gets distorted in the presence of an external electric field, and on top of that external electric field, it gets further distorted when the molecule itself is undergoing vibrational motion. So there are 2 concepts which are involved: the distortion of the molecular electric field due to the external field, and the distortion of the molecular electric field due to the internal motion. In a sense, you have seen part of this in a different concept, namely in the dipole moment, where the charge centers simply separate, and therefore the dipole variation is what is studied in absorption and emission spectroscopy. On the other hand, in Raman spectroscopy, it is the polarizability which results in what is known as an induced dipole moment, and the extent of the induced dipole moment is directly proportional in the linear approximation. So what we wanted to do is basic concepts plus Raman spectroscopy in this week's lecture. Some of these ideas are directly given as tutorials, also applied as tutorials, which means you should study them for the exam, and the others are given to you as information. So the first thing we will study is what is called polarizability. And this leads to what is known as the induced dipole moment in a molecule. Mu induced. This is due to the presence of the external electric field. So what is the relation? The simple relation is that the induced dipole moment, which is a vector, is proportional to the applied electric field, which is also a vector. Okay. But the important thing to note is that the two vectors are proportional. That means the proportionality constant can be a constant. That's assuming that the induced dipole moment is in the same direction as the electric field. Therefore, the two vectors are sort of collinear. I mean, they are in the same direction. If it is a constant, the proportionality constant. Unfortunately, this is a proportionality constant, but in the next step I will write this as alpha E, where alpha is called the polarizability of the molecule. Okay. Now, if the alpha is a scalar, quite obviously the induced dipole moment and the electric field are in the same direction. But it does not have to be. The induced dipole moment need not be in the direction of the applied field. Then what happens? Then how can two vectors be related to each other? That's when you need the idea of what is known as a second rank tensor. Alpha is actually a second rank tensor, and the symbol for that is to write two arrows. And in order to make you feel comfortable with that terminology, I must tell you that vectors that we have here are first rank tensors, and scalars are zeroth rank tensors. So, in this mathematical representation of the polarizability as well as the moment of inertia, you will realize when you study more and more that the polarizability and moment of inertia, and later when we study the chemical shift in the nuclear magnetic resonance, when at a later time that I will give a course on that, the chemical shift is also known as, is also related to what is called the chemical shielding tensor, which is also a second rank tensor. Okay. Therefore, things get a little more complicated as we go higher up in the understanding of these concepts and we start exploring them, but you don't need to get very worried about what is a tensor, how do I understand it. Okay. So, the rest of this 5 or 10 minutes that I have, I will explain to you what is meant by the tensor, not how do we get to a tensor and so on, just to give you an introductory concept. Okay. Here, all of you know that in 2 dimensions you have 2 mutually perpendicular axes, x and y, and any point in the coordinate plane, that is in the 2-dimensional plane, represents a vector which is pointing in this direction, and if you write the coefficients as or x and or y, okay, the x coordinate is the projection of the vector r, which is from 0, this is the 0, 0, the origin. The projection of r onto the x-axis gives you the length rx, and the projection of r onto the y-axis gives you ry. Those are the coordinate points that you have been plotting in 2 dimensions. Now, if instead of this xy axis, suppose we use a slightly rotated axis by an angle theta. That is, the xy axis is, the axis system is rotated by an angle theta, which means this new y prime and the x prime, okay, or an angle theta from the old x and y. Now, what is the relation between x prime, x, y prime, x and y prime, x and y? what is the relation between x prime and x and y? These are unit vectors. You can write x as a unit vector, and Rx is the number that multiplies the unit vector to give the component in the x direction, and then to that you add the vector that is along the y-axis by multiplying the unit vector along the y-axis with the magnitude Ry, and you add that the triangle, the parallelogram law tells you, or the triangle, whatever it is, Pythagoras theorem, all these things, they tell you essentially what is the vector R is. Okay? So if you write the vector R in this notation, it is Rx times x unit vector plus Ry y unit vector. Okay? Now x prime is now the unit vector in this direction, and obviously it has components in both the directions of x and y. Therefore x prime has components in both these directions. Therefore the best way to write x prime is to write the scalar product of x prime onto the x axis times the unit vector x plus the scalar product of x prime onto the y axis times the unit vector y. Exactly the same way you would write to the R quantity this way. So in a coordinate rotation, this is nothing but cos theta times x plus sin theta times y. The scalar product between these two vectors x and x prime unit vectors is, of course, the magnitude of x times the magnitude of x prime times the cos theta, the angle between the two. Well, given that, since the magnitudes are all 1, you have cos theta times x and sin theta times y. And likewise, you write y prime as minus sin theta times x plus cos theta times y. Now this is the property of the rotated coordinate system and its relation to the unrotated coordinate system. Okay? That is, under coordinate rotations, the quantity x prime, y prime, the two unit vectors are connected to the two unrotated coordinate system by this matrix relation minus sin theta cos theta times x y. All are unit vectors. So yeah, you have them there. Okay. This is called the rotation matrix, actually about the z-axis, which doesn't exist in this plane, but it's an axis about which is perpendicular to that, because the rotation is happening in plane, and the rotation basically tells you that the rotation axis is perpendicular to the plane of rotation. Therefore normally we write this as rz theta, but the z coordinate doesn't exist in two-dimensional plane. It's basically perpendicular to the plane. Therefore what is a vector? Any pair of quantities x and y now will have a new component, or x prime and or y prime, because the axis system is now the x prime and y prime. The relation between or x prime or y prime and or x and or y, if this relation is the same relation that you have there, cos theta sin theta minus sin theta cos theta, then the two quantities Rx and Ry are said to be components of a vector. This is the definition of vector, not something that you call as a quantity with a direction and a quantity with a magnitude. And that's how you get introduced to the elementary idea, but a proper mathematical definition of a vector is vectors are the number of components of a given quantity whose transformation property from one coordinate system to another coordinate system is identical. This matrix, this is the transformation matrix that takes Rx or y to Rx prime or y prime. This transformation property is identical to the transformation property of the coordinate systems themselves. The unrotated coordinate system to the rotated coordinate system whatever matrix that transforms the coordinate system, if it also gives you the new vector quantities from the old vector quantities of any pair of numbers, then those pair of numbers form the vector. This is the definition. In 3 dimension, you have to add the z axis to it, and then what is meant by a rotation in 3 dimension is slightly more complicated than a rotation in 2 dimension, because a rotation in 2 dimension involves only one angle. A rotation in 3 dimension involves 3 angles, and these are called Euler angles. Therefore, let us get to the point, even with this 2-dimensional representation, what is meant by a second-rank tensor in a 2-dimensional system. In a 2-coordinate system, x and y. The second-rank tensor is essentially 4 components, and in the case of coordinates, the components are written as xx, xy, yx, yy. They are the products, the regular multiples, and these 4 components under coordinate rotation by the same value of theta, these 4 components become, the 4 coordinates become x prime, x prime, x prime, y prime, y prime, x prime, y prime, y prime, and there is a rotation matrix. And these are called the unit tensors in the second rank, in the unit tensors of second rank in the 2-dimensional system. And therefore, any quantity which has 4 components, whose properties under coordinate rotation follow from the 4 components in the unrotated directions to the 4 components in the new rotated direction, and connected by the same rotation matrix as the rotation matrix that connects the coordinate systems, those 4 quantities are called components of a second rank tensor. These 4, the same rotation matrix, ditto, and they are connected to the unrotated components xy, x, and yy. Okay? These are called the second rank tensors. And what is this rotation matrix and this rotation matrix? I mean, what is it? So compared to the rotation matrix 2 by 2 that we talked about, there is something called the direct product of, let me go to the side, something called the direct product of these rotation matrices. I'll be done in another 3 minutes, so that you should get a picture that if you take a matrix A11, A12, A21, A22, the direct product of the matrix with, for example, itself, let's write another one, B11, B12, B21, B22 is equal to A11 multiplying all the 4 as 4 elements, B11, A11, B12, A11, B21, A11, B22. Let us sort of put a mental partition so that we know what we are writing. And this set of the 4 elements are obtained by multiplying A12 with all the 4 elements here. Therefore, you get A12, B11, A12, B12, A12, B21, and A12, B22. And the lower 2 elements are A21, the second row, multiplying all the 4 elements, A21, B11, A21, B12, A21, B21, A21, B22, and the last set is the second row, second column, A22, B11, A22, B12, A22, B21 and A22, B22. This is called the direct product. This symbol represents the direct product of two matrices. Okay, matrices. Now, what you have to do in order to get this rotation matrix is to do the direct product of the two rotation matrices that you had, namely the one rotation matrix cos theta sin theta that you had. So you would write this as cos theta sin theta minus sin theta cos theta, direct product of cos theta sin theta minus sin theta cos theta. Okay. Therefore, if you took the direct product of this, you will get a 4 by 4 matrix, of which the first two, this square is cos theta multiplying all these 4 elements, the next is the sin theta multiplying all the 4 minus sin theta multiplying. So that is known as the direct product of rotation matrices, and this direct product defines the components of a second rank tensor. Under coordinate rotation, the unit tensors, the coordinate the coordinate system defining these unit tensors will undergo transformation to give you this, and therefore any pair of 4 quantities that you have vectorial in one dimension, the 2 quantities can be vector. Therefore, any pair of 4 quantities which follow the same multiplication property for coordinate transfer is known as a second rank tensor. The same idea when it is extended to 3 dimension with the help of a 3 by 3 rotation matrix, because you have x, y, z, it is known as a second rank tensor in 3 dimensions. So what I would suggest to you is to try out as an example, what is the direct product of this one. What is the result? Do this multiplication, and I will give you one more, which is cos theta sin theta 0 minus sin theta cos theta 0 0 0 1 with itself the same matrix. Put the same matrix here. So with a simple practical exercise of this kind will give you some confidence in the elementary mathematics associated with what are known as tensors. And therefore, now you see in 3 dimensions that instead of 4 quantities that we talk about in 2 dimensions for the second rank, it will be 3 by 3 multiplying 3 by 3, and therefore you will have 9 quantities known, namely xx, xy, xz, yx, yy, yz, zx, zy, zz. How do they transform during coordinate rotation to the 9 quantities x prime, x prime, x prime, y prime, x prime, z prime, y prime, x prime, y prime, y prime, y prime, z prime, and z prime, x prime, z prime, y prime, z prime, z prime. And correspondingly, like moment of inertia, the polarizability, the chemical, the shielding tensor, all have 9 components, but they have additional special properties called they are all symmetric, and therefore what happens is certain components are equal. And finally, you realize that the concept of tensor is ultimately to find the correct direction in which we have the minimum set of measurable, experimentally measurable quantities, and those are called principal moments of inertia, principal values for polarizability, and principal values for chemical shielding tensor. Okay. We will use some of these ideas in the next lecture in determining what is known as the Raman effect. Therefore, this is a preliminary lecture. This is not part of the examination for this course, but this is something important for you to understand if you want to know more about spectroscopy in the future. Thank you very much.